So, I thought I would talk about programming assignment 3 conceptually and like tie these concepts back to the what you have to do. For those of you that are still working on this, so it's Wednesday. So if you're still working on it, you're probably stuck. So what do you have to do for this assignment? So first off, concepts, and then I'll tie it back to what you have to do. So we're covering this concept, actually a couple different concepts in this programming assignment, and these are pretty hard to grasp concepts at first. These are classification and cross-validation. Also a bit of k-nearest neighbors, which you don't really need to understand in depth because it's implemented for you, but you should understand at some level. Okay, so first off, classification. So what do we have for data? Let's describe this data. So we have pictures of drawn digits. So like 9, maybe I'm terrible at drawing, so it's like this, and somebody draws a 1 like this. These are from zip codes that have been written on letters that have been scanned by the post office. So these are like pictures, pixels and everything, pictures of digits. So we have all of these drawings, and the digits go from, let's say this is another picture, the digits go from 0 to 9. So you can map this to grayscale. So grayscale just says, so in this case, it's 28 by 28, I think. 28 pixels by 28 pixels. Each of these pixels gives an intensity value between 0 is completely black to 255, which is completely white. And then in the middle, 100 would be somewhere grayish. So you can take this picture and you can map it to, you can represent this picture using the pixels as 28 times 28 values between 0 to 55. Notice that each of these is a byte. So this is 2 to the power 8. 2 to the power 8 is 256. So you can represent this as a sequence of bytes. So what you can do, instead of representing it as a table, a matrix like this, where you have 0, 1, 2, 0, 0, 1, 1, 255, and then et cetera, that would be a picture. Let's say a 9, this would be a white spot here, another white spot here, etc. Instead of representing it this way, you can represent it, you can flatten. So you can just scan along here, and you can represent it as 0, 1, 2. So for this case, let's say if this were 4, 3, 255, 0, 0, right? And then it continued. So if this were the picture, these are the intensity values at different locations in the picture, then you can flatten this and represent it as 0, 1, 2, 0, 0, 1, 1, 255, etc. And then you continue. So you continue at the next line, 4, 3, 255, right? And so it's just one long string starting at the top, going to the right, and continuing along. So this thing here we call feature vector. So it's just a representation of the object that you're looking at. So the object here are pictures of written digits, and we're representing it using this long list. So this list is going to be of length 28 times 28. It's going to have 28 times 28 values in the list. So 28 times 28, that is, what is it? 784, right? So the length of this list is 784. So what do we have? So in digits.txt, we have a bunch of lines, right? And each line has a sequence that looks like this. It looks like 0, 1, 2, whatever. I'm just going to make something. 1, 255, 100, 104, and they're separated by spaces. And if you look at the number of these 0 to 255 values in the line, it's actually not 784, it's 785. So what this line actually is, it's 784 of these values, and then the last value, this is kind of confusing part of the data representation, is the label. So the label, so let's say this over here, this data here represented a picture. So let's say the picture, this is a picture of a squiggly 9, right? Like somebody drew a poorly drawn 9, but it's labeled as a 9. It's pretty clearly a 9, right? So the label here would be 9. And then the next line would have another picture, a representation of a picture using numbers, using bytes. Each of these are 0 to 55. So let's say the next line is like 1, 1, 2, 0, 255, 127, right? And there are 784 of these values, 28 by 28. So 784. And then we have the label here. Let's say this one looks like, if you were to draw out, if you were to take these bytes here, take these long list of bytes, flatten them into an array like this, into a matrix like this. So take the first 28, put it on the top, next 28, put it on the second row, etc., and then display that using some program. Just like look at the pixel values. Let's say it looked like a 3, like a poorly drawn 3. That kind of looks like a 3, right? And so let's say a person went through this and they said that looks like a 3. And so this is what digits.text looks like. Okay, so that's your input data. And now, what is classification? So classification, you train a classifier, right? So training a classifier involves looking at examples of, let's say, in this case, images and labels for images, and then training some algorithm. So this algorithm will look at these examples and it'll say, this is this, this is this. Well, on a future example, based on what I've seen in the past, if I see something like 0, 1, 3, it's almost the same as this. It's very similar, etc. But it doesn't have a label, right? Let's say this picture here, it looks kind of like the 9 we've seen before, but it's a little bit different, right? So this classifier takes in this data. It takes into account like the structure of these images, and that corresponds to a label of 9. It looks at a future example and says, well, this future example looks similar to the 9 I've seen before, so I'm going to call it a 9. So the algorithm, a classifier, should be able to take examples that don't have labels, that it's not given labels for, and give the label for those examples. So the algorithm will give a 9. So, right? So a 9, let's say this 9 doesn't look the same as this 9. It's slightly different. It has a little thing here. The algorithm will say, well, that's close enough to something I've seen before, so I'm still going to assign it a 9. So that's what a classifier is. It takes examples with labels. So let's say pictures of 9s or pictures of 9s, 1s, 3s with the actual number that's labeled there. And then it looks at the structure, and then it can classify future examples. So that's already done for you. There's this thing called KNN, this classifier KNN, that all it does is it takes the way it classifies held out examples. Held out just means examples that it hasn't seen before. It looks at the picture, this new example picture. It compares it to the previous pictures it's seen, right? So it compares this to the 3, it compares this to the 9, and it gets a score for each of these. So when it compares this 9 to the 9, the distance between them might be like 0.1. So when it compares the old 9 to the new 9, let's say the new 9 looks similar but it has a little squiggly, then the distance is 0.1. When it compares the old 3 that it knows is a 3, this is labeled as a 9, this is labeled as a 3, and when it compares this to this thing, it has to figure out what it is. Let's say this comes out to a 10. So they're far away. The distance between them is big. So this comes out to a 10. And so what the algorithm says is, well, let's say I've had these 2 examples in the past. I compare this to each of these, and this one's closer to this old case I've seen. This case was a 9. So I'm just going to predict that this should be a 9. Right? That's what the algorithm does. That would be one nearest neighbor. So it goes through all of the data you've seen. It finds the closest example to the image that you want to classify, that you don't know the label for. And it gets the label for that example that you know. So you have known cases, the unknown case, and you want to find the label for the unknown case. So that's classification. Now that we understand that concept somewhat, let's build on some of the, let's build on it a little bit more abstractly. So another way to visualize this is, let's say we have labeled examples. So we have right? These are pictures. These are pictures. Whenever I draw a box around a number, that's a picture. It's represented by a sequence of bytes, right? And let's say the 3's over here. So these are poorly drawn 3's. And so let's say we have labels for these examples. So some person went over, looked at this image, and said it was a 9. And they said this is a 9. So this is a 9. And this is a 3. This is a 3. This is a 3. So we also have 2's. So we draw 2. Another 2 looks like. Another 2 looks like this. Right? And so let's say these are also labeled as 2's. So we get a new example. Let's say it looks like this. Right? So it looks like this. So what KNN will say is it will compare this 2 to, let's say we're doing 1n. So we said it'll compare this 2 to every single one of these examples. It'll see, okay, is it close to this? Is it close to this? Is it close to this? Etc., etc. It'll find the one it's close to, and it'll predict the label. It's pretty simple. So let's say 2n. So what 2n will do is it will compare this to all of these. Let's say the closest examples are this guy and this guy. So closest means their distance is the least, so you can just take some distance between these. So the closest examples are these guys, right? So it takes 2 closest examples, it looks at the labels for those, and it finds the most common label. So in this case, the labels are 2, 2. So the most common label among 2, 2 is clearly 2. So let's say we did 3nn. 3nn. This would find the 3 closest images. So let's say one of these 3's looked kind of like a 2, right? Somebody drew a 3 like this, and it looks kind of like a 2. So let's say the 3 closest images to this 2 here are this, this, and this. So it takes KNN, 3NN in this case, we'll take these, let's say these are the closest images. It will take the labels for these images, 3, 2, 2, and it'll find the mode. The mode is just the most commonly occurring element of some set. So in this case, the mode here would be 2, because there are 2 2's and 1 3. 2 is the most commonly occurring element. Okay, so that's what KNN does. And so this allows you to take examples you haven't seen and classify them. That's great. Okay, so how do we, you have KNN already implemented. You can just give, actually this isn't, you can give a K here, which is the 3 or 2 or 1 for KNN, and this will determine how the algorithm predicts new examples. So if you give it a 3, it'll take the 3 closest examples, it'll take the labels for those, and it'll make predictions based on those. So in this KNN fit is this code that takes the train data, is the data you have labels for. So in this case, the train data would correspond to this data here, not this guy, right? The train labels are just the labels corresponding to each of these little train data points. The test data would be this example that you don't know the label for. And we'll get into the test label after. And then K here is the K we've been talking about in KNN, right? So this is 3NN, and then generally you have KNN. Okay, so now let's talk about what you're doing for this assignment is you're taking a classifier that you're given, this KNN fit will run some classifier, and you're to evaluate the performance. So I'll get to that in the next video.